So it's always interesting when mathematicians decide to study something really dumb. Like, if I trip over and roll down a hill, I'm stupid, but at least I get to the bottom of the hill. If we want to make something really small, like the stupidity of a computer, for example, then we can set that to the height of a virtual hill and pretend to roll a ball down it. And so this is machine learning in a nutshell, but we're not going to be talking about machine learning today. And that's because I'm a hipster and machine learning's been covered a bunch before. What I want to talk about is less well known than machine learning, but it has an even dumber origin. And if that wasn't enough, it allows us to do some pretty magical things to the digital media that we all love to consume. So get ready. The game Guess a Number Between 1 and 100 has to be one of the dumbest children's games in existence. The rules are in the title. I come up with a number and you guess what it is. So you can just guess all the numbers individually, so one by one. Though that does take a whole lot of time. Like, I've decreased it from 100 to 10 and it's still taking ages. But really, that's the whole point of the game itself, just to waste time. It truly is the dumbest children's game. And we're still going. And finally. But if you're not using the game to burn time on a road trip, then there is actually a strategy that'll make things a bit faster for you. You can instead start to ask sweeping questions. Like in this case, is the number greater than 5? And then, given that it is it greater than 8? Okay, so is it greater than 7? And finally, we get the answer after just 3 questions. That's a lot fewer than the full 10 that we had to ask before. Okay, let's set the stage for our application. Let's say that we want to record a signal. This could be anything like video, audio, all that kind of stuff. In the real world, the signal is continuous. However, it would take an infinite amount of computer memory to store a continuous signal. So we just can't do that. What we can do is sample the signal at a lot of different points in, like, either time for audio or space for pictures. It isn't ideal, but if it allows us to capture something without an infinite amount of memory, then that has to be a good thing, right? In fact, it's even better than that. Let's imagine your signal was an oscillating wave. Then all you really need is enough sample points to show that the signal is oscillating from positive to negative at a particular frequency. Since there are 2 peaks every cycle, so one positive and one negative, this means that you need to sample at a rate of twice the frequency of the wave. Now, a real signal will be made up of a lot of different oscillations. We can see which frequencies of oscillations are present in any particular signal by taking its frequency transform. So this signal has a lot of oscillation at low frequency and basically nothing after 0.4 Hz. So from before, to represent the whole signal, we'll need a sample rate of at least twice of 0.4 Hz. So this sample rate of 0.8 samples per second is what's called the Nyquist rate of our signal. So let's say I wanted to take a picture of myself wearing a fancy hat. Inside your camera is an array of light sensors, which I've drawn as circles. Light passes through a lens, which I've been too lazy to draw, and these sensors will detect which color it is. So the Nyquist rate puts a limit on the number of sensors you actually need. But if you have a 10 megapixel camera, you still need to cram 30 million sensors into your camera. Now, this is fine if you're just taking a normal picture on your phone. Like, engineers know how to make these sensors really, really small now. But if you wanted to take a picture of me in some exotic color like ultraviolet or infrared, this might not be possible. Like, what if the sensors can't be made that small? or if they're just expensive to make. So the question is, are we able to sense a signal in fewer measurements than set by the Nyquist rate? And the answer is no. The Nyquist rate is a hard limit that cannot be beaten. But maybe our question is wrong. Like, it would be good if a microphone could pick up on the harmonics of my voice, but it doesn't need to perfectly capture the hum of the computer in the background. You see, the signals and media that we're actually interested in measuring are not just random noise. They generally have some defined structure, and if you know what that structure is, you can generally measure it in a smaller number of measurements than you normally would be able to. A technique like this is called compressive sensing. It's compressive because it's capturing incomplete information, and it's sensing because, unlike regular compression, the signal that we're interested in hasn't been fully recorded yet. But I know what you're thinking. Hey, do I look like I know what a JPEG is? Well, maybe we should talk about that. So here's that same picture of me wearing a funny hat. Something that you may or may not be aware of is it isn't just random TV static. My face, my hat, my shirt, the background, they're all solid objects. And like, it helps that I'm a cartoon, but it's true in real photos too. Like, you wouldn't expect the sky to have like weird Technicolor zigzags in it or anything. You'd expect it to stay blue. This interesting fact about real-world photos has other implications too. Like, if you take a frequency transform of a photo, and yeah, that is something we can do, most of the frequency transform is just black, so nothing, with a few bright spots. This is like a signal being mostly zero, but with a few pulses in it. We call this kind of property of signals sparsity. So we'd say that the photo is sparse in the frequency domain. In fact, you can hardly see anything here. I'll zoom in and up the contrast so it's a bit more noticeable. But this kind of sparse property can be exploited. We can write down all the locations of the bright frequencies and then assume all the rest are black. We can then frequency transform the frequency transform to undo the original frequency transform and transfer us back into the regular spatial domain. And you can see that this technique works quite well. This is actually pretty much how JPEG works. Well, there are some extra tricks that JPEG uses, but this is the main idea. One thing to note though is that while this is compression, it's not compressive sensing because we had to actually analyze the image that we were looking at before compressing it, just to work out which frequencies were important and which ones weren't. So we needed to have measured the full image in the first place. Now this is where everything comes together. We know that signals that have a particular structure to them are generally sparse in a specific domain. So let's see if we can find a technique to efficiently measure sparse signals. As the simplest possible example, what if our signal was just one pulse? Well, then measuring the signal is just finding out where the pulse is. And guess what? We can use exactly the same technique as we used in our dumb children's game, guess the number between 1 and 100. Like, does the pulse come after 5 seconds? What about 8 seconds? After 7 seconds? And just like that, we found the pulse. And using only 3 measurements instead of 10. The maximum number of measurements, by the way, would be 4, because that's how many times you can divide 10 by 2 without getting into, like, fractions. Okay, so we're up to a good start with the toy model, but there's still some work to do. Firstly, we need to translate our children's game questions into something that a real-life sensor can actually do. Secondly, it's okay to assume that our signal will be sparse, but assuming it only has one pulse is a bit much. Our technique should work with multiple pulses. Thirdly, we should find a mathematical model for this process rather than just, describing it in the words of a children's game. So let's go back to the drawing board. So we can no longer ask if the pulse comes before or after 5 seconds, because there are multiple pulses. Like, which one are we talking about? What we can ask, though, is how many pulses come after 5 seconds. But remember, these questions are ones that, like, physical sensors need to be able to ask. Maybe we should start with a simpler question. Firstly, how many pulses are there in total? To get our answer, all we have to do is sum up all of the different amplitudes of the different samples in the signal. Most of them are 0, but a couple of them will be 1 where the pulses are. We can write this expression in like a simplified mathematical form like this. If you haven't seen the weird E looking thing before, that's just the Greek letter sigma, so the letter S, which means sum up everything afterwards. So it's just saying sum up all of the signal amplitudes, like as I was saying before. Okay, we're now ready to ask the harder question. How many pulses come after 5 seconds? To answer this, it would be really useful to look at a modified signal, where all of the pulses that come before 5 seconds have been removed. Then you could just sum everything up like before. A trick we can use is to use something that I'll call a window function. So basically, it's one where we want to count the pulses, and 0 where we don't. So if we multiply the signal with this window function, point by point, before summing, then we get exactly the answer we want. So can we actually make these window functions like with a physical sensor? Well, it turns out we can, and I'll show you an example of that later, but it's not even 100% necessary. But before we get to that, let's continue on a bit. So the next question actually might be a bit harder to ask with a window function, because like in our guess the number example, this question actually depended on the answer to the previous question. So for example, like if the pulse did come after 5 seconds, then we need to ask whether the pulse is after 7 seconds now. But if it wasn't, then we need to ask whether the pulse was after 2 seconds instead. The trick is that we can actually ask both these questions at once with a single function. And we can get our count by multiplying and then summing just like we did before. And so we can just continue along, making up more window functions for more questions. So we have our mathematical model. So what is it telling us? So there are two big things I want to point out, and people who have done higher level maths may have noticed it already. Firstly, all of these window functions are waves. They're like just square wave oscillations. And so with this in mind, what we're really doing when asking these questions is taking a frequency transform, or at least an incomplete one. In fact, the expression we wrote down is exactly the expression for a frequency transform. Now, you're absolutely able to take frequency transforms in real life. Like, radios do it all the time, and so do your ears when listening to music. The other thing that I wanted to point out is that this is just an equation where you multiply a matrix with a vector. Like if you're familiar with those terms from linear algebra, if you've done that before. So you're probably asking, like, what does this have to do with vectors and points in space? And the answer is actually, well, everything. But before we look at that, I kind of want to show you an example, because otherwise I'll just lose you in all the abstract nonsense. So remember before, we wanted to take a picture of me with a stupid hat on. But we wanted to do it in a weird color like ultraviolet, where it's hard to make a lot of different sensors. So what we can do is we can replace our whole array of sensors with just a single sensor. And that's why this technique is called a single pixel camera. So instead of the image being focused on an array of sensors, instead it's focused towards an array of mirrors. These mirrors then reflect light onto the one sensor. The trick is that any of the mirrors in this array can actually be controlled to point towards or away from this sensor. This is like the physical manifestation of the window function, where you can select exactly what pixels you want to be measured. The technical name for this is a digital micromirror device, and they're also used in digital projectors. So the simplest thing you can do with a DMD is scan across every single pixel, reflecting one mirror into the sensor at a time. But this is going to be extremely slow. I mean, look at it right now. Remember that the frequency transform of a photo is going to be sparse. Also remember that you can construct a sparse signal by taking an incomplete frequency transform of it. This means that we can find the full frequency transform of the image just by subsampling random positions in space. This is a lot faster than sampling every single pixel. In practice though, you can also get good results just by using random window functions. In fact, compressive sensing generally works better when you just make all your decisions randomly. So like before, when we were sampling pixels, it wouldn't be a good idea to just take all of the pixels from the top half of the picture. Otherwise, we wouldn't be able to figure anything out about the bottom half. So it was at this stage of the video making process where I'd already done all of the animations, and I realized, oh yeah, I should really do like a demonstration of this working. So I kinda did it in the laziest way possible. So like it only uses generic Python libraries, stuff like that. So like, if the last animation was a bit confusing, here's the basic strategy. We sample a random selection of pixels in the image. We then find the sparsest possible frequency transform that's consistent with the pixels we captured. Finally, we can frequency transform back to get a complete image. So here we've got a picture of me in a fancy hat again, and we've also got this subsample where we haven't taken all of the pixels, like all of the black ones, we just don't know what they are yet. And so we can take the frequency transform of this. Now, there are a lot of possible frequency transforms which are consistent with all the pixels we know of so far. But we know that because it's an actual photo, well, kinda, the frequency transform should be sparse. So we find the sparsest frequency transform that's consistent with the data and just transform back. And yeah, it works pretty well. So that was the fun demonstration of the day. Now back to the maths. So far we've been drawing these signals out as dots, but another way to think of them is like a list of numbers representing their amplitudes. And so this list of numbers changes as the signal changes. Now the trick is you can think of this list of numbers as a point in a really high dimensional space. Like in 2D you have 2 coordinates, but we just keep on going here. In fact, we can represent a very simple signal like this as a point in 2D space. See how changing the first sample moves the point along the horizontal axis? Moving the second sample moves the point along the vertical axis. Importantly, look at what happens when the signal is sparse. If the signal is sparse, then most of the samples will be 0. This means that the point will lie on an axis. Okay, so we explained the vector part of it. What about the matrix one? Well, if you have a point in space, then you can kind of pick your axes arbitrarily. So a frequency transform is just like another set of axes you can choose to measure your signal in. But if you take an incomplete frequency transform, then like your signal could be any one of these points along this line basically. Like any of them are consistent with what you've measured. But the trick is, we know that our signal is sparse, and there's only one sparse signal along this line. It's the one over here. So all we have to do to get our signal back is find out which signal along this line lies on one of the axes. Now if you think about it, a sparse signal is quite small in a sense, like it's only a couple of pulses. So maybe we could get a clue of how to find our sparse signal by looking at all the sizes of each signal along this line. Imagine you wanted to get to a point in a park. The size of the path you'd have to travel is just the straight line distance. And you can just find this out with Pythagoras' theorem. You can use Pythagoras' theorem to figure out how big a signal is as well. Coincidentally, if you use this method to figure out the size of a signal, then you're basically just finding the signal power, so just like how much energy it uses when traveling through an electric wire. So let's have a look at our line of possible signals again. If we draw a line from the origin to a point in our possible solutions, then the length of this line will just be the signal power. Well, the square root of it anyway. Let's try and find where the signal power is smallest. Did you miss it? That's okay, let's plot it out. Okay, you can kind of see it now. Another trick we can use to find the smallest signal power is to get a circle and increase it in size until it hits the line. This is because a circle is the shape of constant signal power, as in every point in the circumference is just one radius away from the center. So we found the point of smallest signal power, but it's not very useful because it doesn't intersect an axis. But we don't have to give up yet. There are multiple ways of measuring the size of a signal. Okay, imagine now I'm in a car instead of just walking. Now I have to travel along the road instead of just going cross country. The size of the distance I travel is the distance along each of the roads I go along. Or in general, the distance along each of the axes I must go along to get to the point I'm looking for. So this way of measuring size can be called the taxicab distance or Manhattan distance. Let's see if we can find the solution on the line with the smallest taxicab distance size. So this size is just the length of the path of these two perpendicular lines. We can again just plot it out so it's easier to find the smallest signal. That looks promising. Now the equivalent of a circle for the taxicab distance is this diamond. And we can see the signal is smallest where the diamond touches the line, and this is on an axis crossing. So we can find the sparsest signal by finding the signal on the line with the smallest taxicab distance. Okay, so we just need to find a way to make this taxicab distance of the signal as small as possible. I wonder how we... So, ladies and gentlemen, we've come full circle. We can just pretend it's a hill and pretend to roll a ball down it. So that's compressive sensing, a dumb children's game extended by ridiculous levels of high-level maths. So if you're ever feeling dumb, just look at what this dumb children's game was able to do. So that's the video, everyone. It was made by me, and it was inspired by the Summer of Maths Exposition number 2. I don't know if it turned out that well, but if you like it, I have more ideas, not necessarily maths, but more of STEM. So give me feedback, like and subscribe, all of that stuff, and thanks for watching.